Thermodynamics, Entropy, Free Energy, and Equilibrium, Chapter 16. So in studying thermodynamics versus kinetics, when we looked at kinetics, we studied rates and how we can affect how fast a reaction will occur. And kinetics, it depends on the mechanism. So it depends on the pathway from reactants to products. When we look at thermodynamics, we're only looking at the properties of our reactants and our products. So not how they get there, just what are their energies, what are their entropies associated at that particular time. So where we start and where we finish, thermodynamics. This middle part here where we get up to our intermediate, this is where we study kinetics, the pathway. So in studying initial and final states, that takes us back to last semester when we learned about enthalpy and state functions, right? A state function only depends on the initial and final state. So enthalpy is one. We're going to study entropy, Gibbs free energy, change in temperature, change in pressure, change in volume. Those are all state functions. So a review, because we did study a little bit of this last semester. Spontaneous processes and entropy. So you can predict whether a process will occur, but it gives no information about the amount of time required. And a spontaneous process is one that occurs without outside intervention. So it just happens on its own. These processes can be reversible or irreversible. For example, reversible would be the fact that you can freeze water and then you can melt water. We see entropy changes with those. And depending upon what state you are in, it is spontaneous to freeze water if the temperature is low enough. It is spontaneous to melt ice if the temperature is high enough. But that is a reversible process. An irreversible process is one that you cannot go back. Any example of this would be anything that's decaying, anything that's spoiling in terms of food in your refrigerator. Once it's gone bad, it can't go back. So those are a couple examples. So entropy is given the capital letter S, and it is a driving force for the spontaneous process is to increase the entropy of the universe. So even though overall the entropy of your system may be decreasing, that means then that the entropy of your surroundings must be increasing enough to balance that out such that the universe constantly is gaining an amount of entropy. And entropy simply measures molecular randomness or disorder and the number of arrangements that are available to a system existing at a given state. So easy way to think about this, if you have 10 pennies, and you arrange the pennies in all the possible ways that they can be arranged versus heads up or heads down. There's only one state where they are all heads up. There'd be only one state where they are heads down. And so then there's all these microstates in between. And you'll see that the most likely combination, if you have those 10 pennies, would be half of them up, half of them down. So nature tends to move towards the states that have the highest probability of existing. So, for example, the expansion of an ideal gas. So we start off with the gas just in this side of the container. We open up the valve, and we notice that it's going to occupy this side of the bulb with just as many molecules that were found on this side. So things are going to spread out. They're going to disperse because it's more favorable for them to exist in this way. So translational motion would be side-to-side motion. Vibrational motion would look at two atoms connected to each other and how they can vibrate, that bond, those atoms connected to each other, the vibrations that can occur. And rotational motion would look at if we go back to study shapes. So if I have something that's tetrahedral and I were to hold one of those atoms still, so not the central atom, but one of the outside atoms, and then I spin the other ones, that would be considered rotational motion. So clearly, in looking at these, you're going to have the most amount of available motion and states in looking at a gas versus a solid. So here's another slide talking about the microstate. So this goes back to my pennies example. But here we're starting with 4 gas molecules. The likeliness of them all just being on one side versus the other. There are only one of each of those states. Then looking at each individual molecule or atom, we can see that we can have a 3-to-1. We also see that we can have a 1-to-3. So these are the same as well. And then the most likely state to exist is when things are completely evenly distributed. So we have 6 microstates where we have an even number of gas molecules on either side of this piece of glassware. So the gas expands into a vacuum because the expanded state has the highest positional probability of states available to the system. So that sounds really, really fancy, but it just means that given the opportunity, a gas that is in an enclosed container and then that container is opened up, those gas molecules are always going to spread out because it increases the amount of randomness or disorder within that system, i.e. the probability of different states. So because we have the most freedom of movement in a gas, that is where we see the most amount of entropy. And because solids are fixed, those particles are packed so tightly together, here we can only see the potential of maybe some vibrational motion, as opposed to, as a gas, you have translational, rotational, and vibration. So entropy, it's very important in the formation of solutions. So some solutions that we would maybe think, oh, this isn't going to form based on the enthalpy that's associated with it, based on the amount of energy that may be required to make the solution. The increase in entropy outweighs that sometimes. So anytime you make a solution, you take a solid, well, there are different types of solutions, but let's say you take a solid, you dissolve it into some water. So that solid has very little entropy. Your liquid has more entropy, but then when you put that solid in, if it dissociates into ions, now we have many more states available for those ions to be in, opposed to when it was fixed in its solid form. So like I say, some enthalpies for solutions are endothermic, and that would not necessarily be a favorable process, but because we see such an increase in entropy, the solution will form. So if we recall, the first law of thermodynamics says that the energy in the universe is constant. So we cannot create energy, we cannot destroy it, but we can change the way it looks. We can even change it into mass, and mass can change into energy. Second law of thermodynamics says that there's always going to be an increase in the entropy of the universe. Always. So the total energy of the universe is constant, but the entropy is always increasing. So S of the universe equals the change in entropy of the system plus the change in entropy of the surroundings. So one of these might be going down significantly, but that means the other one has to go up just as much and then a little more. So energy is constant, entropy always goes up. So we can look at what is the entropy of the system, what is the entropy of the surroundings. So the sign of the entropy of the surroundings depends on the direction of the heat flow. So the higher the temperature, remember temperature is directly related to the average kinetic energy of those molecules in that system. So the more energy we have, the more they're moving, which means more likelihood of different microstates. So the sign, which means it's either positive or negative, we're either increasing entropy because that would be positive, or we're decreasing entropy, that would be negative, depends on which way the heat is going. If you're getting colder, you are decreasing your entropy. If you're getting hotter, you're increasing your entropy. Now the magnitude of our delta S depends on the temperature. So Very similar here, right? Temperature and heat flow are not the same thing. Heat will always flow from hotter to colder, or we're looking at whether a process is endothermic or exothermic. So this is exothermic, endothermic. This is the temperature with which that particular process is happening. So heat transferred under constant pressure is our change in enthalpy, our delta H. And remember, this is a state function, so this is for reversible processes only. So we have an equation, delta S of the surroundings. We have to keep this separate from the system. Delta S of the surroundings equals a negative delta H over T. And T has to be in Kelvin. So we're going to have to do that conversion. When we're given Celsius, add 273. So our driving force is provided by the energy flow. The magnitude of the entropy then depends on the temperature. So for an exothermic process, the entropy of the surroundings is increasing because the energy is leaving the system, going into the surroundings, which means that these molecules are getting more excited and are moving around. Vice versa, an endothermic process means that the surroundings is losing the energy and giving it to the system. Therefore, those surrounding molecules are quieting down. They're not moving around so much because they've lost some of their energy. Therefore, entropy is decreasing. So when we look at the surroundings, we look at the heat transfer. When we look at the system, we look at positional probability, or those numbers of microstates that we have possible. And entropy is generally dominated by the number of gaseous components simply because there's so much more entropy involved when we have gaseous molecules. So the third law of thermodynamics is that the entropy of a perfect crystal at 0 Kelvin is 0. So everything has entropy, and we still cannot, scientifically, we cannot get down to 0 Kelvin. That is absolute 0. So entropy continues to increase as we increase our temperature. Now, delta H values, your enthalpy values, and then we're going to study here in a minute, our delta G values, or Gibbs free energy values. Those energies of formation are 0 for perfect, or are 0 for elements, anything in its elemental state. But oxygen will have entropy associated with it. It will not have enthalpy or Gibbs free energy. Those would both be 0, but everything has entropy associated with it. Everything has some amount of rotational, vibrational, and translational motion. So entropy is a state function. So we can represent this by looking at a particular reaction. We look at a table to find these values. And keep in mind that this little symbol at the top, that is our S naught, which means that we're under standard state conditions of 298 Kelvin, which is 25 degrees Celsius, 1 atmosphere of pressure. And when we're looking at solutions, we would consider a 1 molar solution to also be standard state. So we look up all the values for our products, we add those up. We look up the values for our reactants, we add those up. And then we subtract the total amount of reactants from the total amount of products. Keeping in mind that each individual entropy value would be multiplied by the stoichiometric coefficient in the balanced equation. So if you have 2 moles of something, you would multiply 2 times your entropy value. So shifting away from entropy, we can look at what we call Gibbs free energy. So Gibbs free energy depends on enthalpy, on temperature, and on the entropy. So we can only be at constant temperature and pressure, so we cannot be changing those. We look at it at in one particular instance. And when we do this equation, we're looking at the system only. So a process at constant temperature and pressure is spontaneous in the direction in which the free energy decreases. So that means we need delta G to be a negative value. So even though entropy can look at predicting whether something is spontaneous, to truly say whether a reaction overall will be spontaneous, we also have to take into account whether or not it's endothermic or exothermic. So if delta G is greater than 0, i.e. it's positive, that is a non-spontaneous process. When delta G is less than 0, it is negative, and therefore it is spontaneous. And when delta G equals 0, that is when we are at equilibrium. So there's no energy change there. We've used up all the energy to get to equilibrium. And therefore, there's no free energy to make anything else happen with that reaction. So getting to equilibrium is not necessarily a good thing. So the delta S of the universe equals delta G divided by T. Keeping in mind we've got this negative sign here at constant temperature and pressure. So how do the signs of delta H and delta S affect our delta G? So if something is exothermic and increases entropy, right? So exothermic means we're increasing the entropy of the surroundings. Here we have a positive value for the entropy of our system. So this is spontaneous at all temperatures. When we have an endothermic process, but we are increasing entropy, an example of this would be when we melt ice. So we need energy to do that, but we're going from a solid to a liquid, so we have more entropy in the liquid state. That is only spontaneous at high temperatures. So melting, we have to be above the melting point, at the melting point or above it. Now, spontaneous at low temperatures would be when we have an exothermic process, but we are decreasing our entropy for our system. So here, if we're melting ice, the opposite would be freezing. So we have to give off energy to let the liquid molecules become a solid. And in doing so, we have more organization in our system. So the entropy goes down, but we're losing energy. So once again, we're increasing the entropy of our surroundings in this. So at low enough temperatures, we can freeze things below the freezing point. Now, not spontaneous at all is when we have something that is both endothermic, which means our surroundings is losing energy and entropy, and then at the same time, our system is also losing entropy. So this will never be spontaneous, which just basically means that this reaction would be spontaneous in the reverse direction. So we can look at standard free energy changes. So when we talk about standard, once again, we get this little not symbol, so we're under standard state conditions. There's two ways that we can calculate delta G naught. So here, we can use our H naught values and our S naught values, and these are all in the appendix, or you can be given a delta H naught for a reaction or a delta S naught for a particular reaction. And you have to be given the temperature, plug these values in, calculate delta G. If it's negative, it's spontaneous. If it's positive, it's non-spontaneous. Similarly to what we've done with enthalpy and then what we saw a couple slides ago with entropy, we can also use our Gibbs free energy of formations. Once again, those are all values that are listed in your appendix in a table, a thermodynamic table. So we look up our products, we look up our reactants, we use our coefficients and multiply each by whatever number we need to, if it's 3 moles or 1 mole or 5 moles. We add those up. That's what this symbol here means. Add them up. We need a total here, and we need a total here. And then we subtract. So either way, whichever way you are given information to solve for delta G naught, they should give you the exact same answer. You can't have a different delta G naught for the same reaction at the same temperature. And as I stated earlier, Gibbs free energies of formation for pure elements are 0. Same thing if this was a delta H naught F equals 0. So pure elements are your diatomic gases, all your diatomics, because bromine is diatomic, but it's a liquid, and iodine is diatomic, but it's a solid. So all your diatomics, and then everything else on the periodic table, when it is in, it's a standalone. It's a standalone solid. Lots of metals, standalone metal. If it's not bonded to anything, it is in its pure elemental form. Now, keep in mind, sulfur can exist as S8. Well, sulfur is just bonded to itself. It is in its elemental form, one of its elemental forms. So if it's bonded to anything besides itself, it's not an element. Therefore, it has a value associated with it because it had to be formed. So these are energies of forming new things. We just say, hey, elements already exist. We're ignoring whatever enthalpy and free energy went in to create them. So we can look at the dependence of free energy on pressure or on concentration. So these are partial pressures or concentration. So basically you can look at pulling in that reaction quotient Q from what we studied in the chapter dealing with equilibrium. So what happens when we aren't under standard state conditions and we don't have things that are just 1 molar or under 1 atmosphere of pressure? How does that change everything? So we once again have another equation which we need to have our delta G naught, which we can calculate from energies of formation. R is the gas constant in terms of energy, which means that it is 8.3145 joules per Kelvin mole. Temperature has to be in Kelvin. So we can use this equation to look at what is the delta G for a process when we're not under standard states. So free energy and equilibrium. The equilibrium point occurs at the lowest value of free energy available to the reaction system. So once again, delta G is 0. So in this particular graph here, our equilibrium lies closer to the products when we're looking at how much of A has reacted. So in this instance, it is a spontaneous process because delta G is less than 0. And then our equilibrium constant is greater than 1. So both of these say that the reaction favors the products. It spontaneously occurs, and K is big enough to show that we favor products. Now, what happens when delta G is positive? Well, it's greater than 0. This is a non-spontaneous reaction, which agrees with the fact that K is less than 1, which means that we favor the reactant. It's non-spontaneous, favoring the reactant, so this reaction is not very likely to happen. So our equilibrium lies closer to our reactants. We hit that equilibrium position first when our K values are extremely low. It takes a while to hit equilibrium when our K values are really high because we've got to make so many products before we can actually start pushing products back to reactants. So mathematically, how does this work out? Delta G equals 0. Not delta G naught. Delta G naught is your Gibbs free energy of formation. Everything has that, okay, unless you're a pure element. But when we're looking at reactions, we're looking at G naught values. So delta G becomes 0. Rearranging this equation then gives us delta G naught equals the negative RT ln of K. So there is a relationship between delta G naught and K. This is negative when this is positive. Or, well, I guess they're both positive. This is negative when your K is really large. When your K is really small, i.e. it has a negative exponent, 7.0 times 10 to the negative 9th, this ends up being negative. A negative times a negative gives you a positive delta G naught, and now we are non-spontaneous. So your delta G naught and your K value should agree in terms of, is this reaction spontaneous because it favors the products, or it's non-spontaneous because it favors the reactants. So this is going to come up in the next chapter when we study redox reactions and we study electrochemical cells, which is basically just looking at batteries. And we know that batteries can do work. They charge our cell phones and our iPads and all those great things. So the maximum possible useful work comes from this free energy change. So Wmax, the maximum amount of work that you can get out of a particular reaction is the amount of free energy available. It's free energy. This reaction wants to go in a particular way based on its enthalpy and its entropy values, allows us to have some energy. that free energy then can be applied to do work, which is make your cell phone work, make your iPad work because of that energy that is available. So keep in mind, if a reaction is spontaneous in the forward direction, it is going to be non-spontaneous in the reverse direction. So we can look at activation energy here. This is a favorable process. It is spontaneous. Small amount of activation energy to go forward, but a huge amount of activation energy to go backwards. Remember, activation energy is just the energy it takes to get to the top of the hill. So in this particular reaction, if we go in the reverse direction, we have to have a lot more energy than what we can possibly get out. So basically, your investment in energy was bad if you do this reaction in the reverse way, because you have to put in a whole lot of energy to get out nothing. Where here you put in a little bit of energy and your net gain is large. So that's the free energy. That energy then is available to do work. So why do we study thermodynamics? Well, energy is one of the driving forces in all of our reactions. So, plus we want to see how can we use that energy to do work. Combustion engines, etc. Those are highly inefficient. But we achieve the maximum work available from a spontaneous process. And so this occurs in a hypothetical pathway. Any real pathway wastes energy. So everything that we do, you're always losing energy, and that energy is almost always lost as heat. So what does this mean? All real processes are actually irreversible. So even the melting of ice or the freezing of ice, you're still somehow losing energy. I mean, think about it. If you're trying to freeze your water and put it in the freezer, you're expending a lot of energy to run your refrigerator just to make a couple ice cubes. So that energy is always going to be lost. You're not harnessing that energy in any significant way. So the first law says you can't win, you can only break even, right? So energy is not created or destroyed, but because we're always losing energy, then the second law basically says you can't even break even. So this is thermodynamics. Now within this chapter, we only saw a couple math equations, so that'll be nice. But what we really need to look at is understanding what is entropy, going back reviewing what is enthalpy, what is this new concept of Gibbs free energy, and how we use that equation of using our standard entropy values or standard Gibbs free energy values to calculate a Gibbs free energy or an entropy for a reaction. It's always the sum of the products minus the sum of the reactants. That never changes. And then we can look at what is the relationship between the entropy and spontaneity, Gibbs free energy and spontaneity. We can study at what temperature certain processes might become spontaneous. And then in the last bit of this chapter, we will focus on the relationship between the equilibrium constant and Gibbs free energy. And once again, that's all tied in. And in the next chapter, we're going to tie in another thing which will agree with both delta G and K, and that is when we study the potential, the electric potential of particular reactions. So good luck studying.